1 second. Okay. Can you hear me, Daniela? I want to make the 0, but you can't. A bit, but it doesn't bother, right? Good morning, Daniela. Quick question. Do you hear like echo of my voice? Okay, cool. Then just all right. We're gonna wait for everyone to be here, and then we're gonna start. I already shared my screen. Okay. Right. Mm. Okay. We'll wait around 2 more minutes to see if other people are joining. Otherwise, we're gonna get going because we have a lot to cover. Hey, Daniela. Well, since no one joined so far apart from you, then we're gonna get going anyways. And well, they know about the time, so we can deal with it. Anyhow, as you know, the exam will cover topics from the midterm as well as for the final. And there are several types. So the way I decided to do this is by going through the theory first, and then eventually you're gonna go through an exam. Yeah. So let's get going. Okay, controls. All right. So first thing we have to take a look at is the Venn diagram, or the Venn diagrams, as well, they don't always appear in exams, but they're very important because they could be like one or two questions. And one of the things you have to keep in mind is De Morgan's law, which means the intersection of the complements of two sets is basically the complement of their union. which makes sense intuitively when you think about it, because the opposite of A, the opposite of B, they intersect, well, outside of both. Therefore, the union of both, the opposite of it is the same. Very clear, very simple. Yeah, and that's the complement. Yes, so in exam questions, you might have a couple of exercises where they ask you to basically draw some of these, and they will give you some sort of formula, and then you draw the Venn diagram. And it's usually around, let me see how many points it is. Yes, 5 plus 6, 11 points. So quite a good sum, huh? Yeah, this is more of the same. Yes, so now we get to relations. So binary relation is a relation of type A, B, A times B, or A squared. And a relation to set A is a binary relation of type A. Well, this is more like predication in English. So if you say, for example, X is brother of Y, both of them are people, they are part of set people. And that's why you say people to the power of 2. Follows course is the same. It's type of predication. We use it in English and any other language as well as humans. And when you say X follows Y, X follows course Y, then Y is always, of course, a course, ironically. And then X is a person, student. Yeah. And the infix notation is basically putting the predicate in the middle, and it's closer to natural language in terms of understanding. Yes, then we have to take a look at directed graph. These are pretty simple. So basically, it's like vectors from nodes. And as you can see with the matrix representation, when you look at the relationship R or the graph R, you see all the nodes and the set. And the matrix representation over here is basically representing which nodes connect to which one. As you can see, A to A, the other one is connected to B, and then it's one, yeah, from to. And this could be well visualized by then using Venn diagrams. And as you can see, you could put two sets as two opposing sets and basically put R as a relationship in between them. And what you, yeah, etc. Yeah. So inverting a relation. When you want to invert a relation, you simply take all the arrows and reverse them. For example, here, as you can see, from A was going to 2, from C was going to 1 and to 2, and here's the opposite. And that basically gives you the reverse of that relation or of that predicate. This brings us to Hesse diagram. And Hesse diagram is basically, I know it sounds a bit complicated, but what it means is basically how the order which in you visit the states. So for example, linear order, binary, minimum hip, etc. Breadth first, you know the deal. And the algorithm, the way it works, and actually this is quite important because it might pop up in a question, and actually quite a hefty one. But it's quite simple. So basically took and what kind of relation you have, and in this case we have is divisor of. And because we have is divisor of, we take all the ones in V that are divisors of other numbers. For example, divided by 1, 2, and 3. Um, let's take an example, G2. So 4 is a multiplier of 2, 6, and 12. However, 12 is not cannot be considered as part of the Hasse diagram. Therefore, you only put 4 and 6. The same goes for 3, 4, and eventually 12. As you can see here, it's actually more intuitive to look at it this way. As you can see, from 2, it's divided by 4, and it's divisor of 6, while 4 is divisor of 12, and 6 is divisor of 12, etc. Oh, someone else. Yeah. Let me record. Go to the cloud. Guys, if you don't mind,
This meeting is being
I'm gonna
recorded.
record this, please, from now on. All right. Then how to order product set. So in this case, we take a look at the problem. What is a natural order of the set A and B? Well, suppose that we have partial orders for A on A and for B. And we can take, for example, this lexicographic order, which basically takes priority over B. And as we can see, it's A, B, C, and 1, 2, 3. And then you start with A, when taking priority means, and then 1, 2, 3. You take for A each of the others from the other set, and then rinse and repeat. This is not very important, as the exam questions would be more about building the Hasse diagram. Yeah, and there's another order. It's basically the same way, but they're saying, hey, we're gonna use a normal order, Cartesian. So 1, 2, 3, A, B, C, 4, 5, 6. That's what they mean. And as you can see, it's presented in the graph here. Yes. So theorem, the Cartesian order is a partial order. I could take A and B to showcase that. Well, the way they chose to prove this is by basically by putting them as dots and chain A, chain and B, and then proving reflexivity, antisymmetry, and transitivity. And this won't be very important as it never happened, it never appeared in the past exams. This, however, is quite the opposite. So an equivalence relation is a relation of type A to A that is reflexive and transitive and symmetric. So for a relation to be equivalent to another, well, for X to be equivalent to X or X to Z, whatever, the relation has to be reflexive, transitive, and symmetric. As you know, reflexive is basically it validates its own, transitive, it validates the next one, like the grandchildren, and symmetry basically goes both ways. Yeah, so logical equivalence means that both sets have the same truth value for every possible valuation. And you say, why? Well, one of the sets always has same truth value as the other, as reflexive. And then we take a look at the property of symmetry, and then it's immediate from the definition that it goes both ways. Positivity. Well, we can see that both sets have the same truth value. And if that set and another one, third one have the same truth value, then the first and the third sets have the same truth value. Well, more examples will include De Morgan's law. For example, the negation of P and Q is similar to not P union not Q. It's the same the other way around. Or disruptivity, or contradictions, these are good examples. These, you would say, these are logically equivalent. Although does it look on a map? So basically, when you draw them, this is how the equivalence relation looks like. So reflexive, symmetric, transitive, and therefore equivalent. And from equivalence, we derive equivalence classes. So these are partitions where they belong to A and they form a distinct class. So for example, if you want to make up a complete system of representatives for equivalence in A, then there could be a set in A that contains precisely one element from each class. So for example, modulo 3 in N. So in N, anything that divide by 3 will basically so basically will result in a 3 at the end. And here we can see that they mapped out 0, 1, 2 as the three class representatives, and that's what they have at the end. We will make this a bit clearer in the exam in the exam later on because it's harder to explain it without a good example. Yes, this brings us to functions, and these are quite important as a lot of heavyweight questions are concerned with functions. And as you know, functions from math or math class or high school. So you take one input and that produces a y, an output. So from x to a y, and it's a binary relation. So it has a codomain and range, and it has two properties. So if the domain basically consists of the entirety, the domain of the function consists of the entirety of the domain of the original set, source set, then we call it total. Then the function itself is called total. If the range itself covers a codomain or basically an entire set completely, then we call it surjective. And injective basically don't like when you look at it, it seems a bit weird and complicated, but at the end of the day, it means a simple thing. If you have the same x, then you should have the same. If you have like equivalent x's, might I say, not the same x, then the functions of those x's will be equivalent. But if the x is not the same, then the function yield shouldn't be the same. So if the x is the same, the y shouldn't be. Sorry, if the x is the same, then the y should be the same. Otherwise, it cannot be. And for surjective, it's basically about the range, as you can see. So I hope this clears it up a bit. Surjection. Yes. So for example, if you take r is any y bigger or equal to 0 with an f of x, basically function b and bx minus 1 absolute. So we know that since it's absolute, then we won't be negative, and we know y is going to be bigger than 0. Therefore, it won't be injective because for each x, there are x's that are different that produce the same y. Yeah, so therefore, you cannot say it's injective. And surjective, we can say that because the entire domain of 3x minus 1 or range of 3x minus 1 is covered here. We can do the same here with z and natural numbers. So this is a very similar function. However, we don't have the restriction of y being bigger than 0. We have restriction of it being part of n. So therefore, this is injective because this function, even on absolute value, it's all natural numbers. And it's not surjective because it cannot cover the entirety of the natural number. So thereafter, we have composition of functions. So this is where it comes in handy because these are the parts that actually come in the exams and they ask you to make compositions of functions. So what does that mean? It's very simple. So I believe you already had an experience in high school, algebra, or on one of the courses you had. So basically, when you combine two functions, you take one function and you present x in it, and then you take that and input it to the next function. So a good example would be g and f, right? Here. So if you look at 1 minus x2, that's f. And then we have g of x is square root of x. Therefore, since we have square root of x and it's g of f of x, then we put the square root of f of x, and that will yield the square root of 1 minus x2, x to the power of 2, excuse me. Yeah. And the domain of both can never be the domain of the function. Both functions can never be the domain of f, and the range can never be the range of g, which makes sense intuitively because this changes the actual domain and range, since you change the expression. Yeah, and then after we have to take a look at inverse functions, which basically means You take a function, then you inverse it. Of course, the inverse if it's injective. And this theorem says the inverse of f is a function if and only if f is injective. So what does this mean? So if f is injective, this means each x produces an f, and the x's have to be equivalent for the y's to be, well, the function output for them to be equivalent. Therefore, when you flip it, okay, I can give you an example to better explain this. Think of a classroom. Okay, each person in the classroom has a grade, right? Yeah, so I have a grade, each other person has a grade. Me, I have one grade, that's it. So me, injective. And if someone else has the same grade, is okay. But if you look at the grade and you look at the other way around, it's not one-to-one no more, it becomes many-to-one. Because each grade can be owned by many people. Therefore, when you inverse, the inverse of a function can be a function if and only if f is injective. I hope that makes sense. Bisections is basically similar to equivalence. Well, basically it says, hey, if the function is total and it's injective and it's surjective, therefore you can say it's bijective function. And of course, bijections have a bijective inverse. Okay, so the next concept we're going to take a look at is cardinality. Cardinality is quite simply what it means and what it entails in English. So cardinality is the size of a set. And we can say that the cardinality of A is less than cardinality of B if there exists a total injection from A to B. So anything in A has something special in B. Unless the two in A are equivalent, then the one both yields in B are equivalent. And if they're equivalent, the cardinalities, then there exists a bijection from A to B. So they're total, surjective, and injective. Yeah. Special case is the finite size. All right, so take a look at the Cantor-Schroeder-Bernstein theorem. So his theorem says if there exist total injective functions f from A to B and G mapping B to A, then there exists a bijection H that maps A to B. And this basically, it's not going to be in the exam, but it's good to know that you can use this theorem to actually prove that it's a partial order on cardinalized sets. Use anti-symmetry and transitivity. However, this part of the course won't be in the exam. All right, this, on the other hand, will. So mathematical induction is a strategy for proving claims. And this strategy is widely used in many disciplines. And the way it works, you take a base case. In this case is, well, it says Sn is true for every integer n bigger than a, right? Bigger, equivalent, or equal. Excuse me. So basically, when you look at Sa being the lowest value that n can take, then we could consider as the base case. And then from there on, we have to assume that Sm is equal to, well, the same equation that you're offered, because at the moment we don't have any equation. But in this case, Sm is equal to Sn plus 1 for any n bigger than a. So we assume that what stands true for the base case stands true for the inductive case as well. And thereafter, we take n plus 1. So n plus 1 is equal to m and then plus the rest of the equation, the expression. And then basically from there on, you start your induction hypothesis. What I mean is, there's an example here. For example, you want for each n part of a natural number set, you want to prove that sigma starting k equals 0 of 2k is equal to n plus 1 minus 1. So here we start with the base case. First thing, we know it's all numbers natural. So since we know it's natural numbers, it can only start from 0. So we take 2k is equal to 2 to the power of 0, which is equal to 1, as you know. And then we take the other side and we calculate it. And it's 2 to the power of 0 plus 1, which is equal to 2 power of 1 minus 1 is equal to 1, is equivalent. So we have proven that this stands for the base case. Now we create an inductive case. And basically, this entails taking exact same expression and changing whatever has n in it to an m. And that's it, as simple as that. And you just say, let m be the same condition and assume. Thereafter, we go to the actual proofing step, which basically we take n plus 1. So we replace n with n plus 1. And then we prove using the expression of n plus 1, as you can see here. So fm plus 1 2k is equal m 2k, which is the one we already assumed here, plus 2m plus 1. Intuitively makes sense because at m you have 2k and then you have 2m to the power m plus 1. And this is equal to basically the other side and then it's m plus 1. And thereafter you just come to the conclusion using your assumption, the deductive step, and then the proving step. Of course, we're gonna do this in practice. For now, it's just theory. And I know it's a lot, but don't have a lot of time. Yes, so this brings us to the well-ordering principle. And basically, this is about lower bounds and how they could be derived. And in this case, as you can see in the examples, we can assume that 0 is a lower bound for, well, the function in z that limits x by being bigger, or yeah, strictly bigger than 0. Is the same case for in Q and R. So the well-ordering principle says every non-empty subset of subset A of Z that has a lower bound has the smallest element in the usual linear order on Z. So basically, any subset that's not empty has a lower bound, and that would be the smallest element usually. And this brings us to the last type of structure we're going to take a look at, and those are sequences. So sequences are similar to matrices or sets, but they differ in the way that they're defined recursively. So what does that mean? So basically, it means that each element is dependent on the element before it. So for example, T1 is based on T0, T3 is based on T2. For example, this could be like Tn plus 1, as we can see here. And there are many types of sequences, and these are a couple of examples, just a couple of examples to make you think about it, but there are many, many types. And as you can see, we have the geometric sequence here where you always have C times R, and then R always just exponentially grows. And factorials, which is quite clear, just factorials, like each number is just over and over. Yeah, Tn factorial of n. All right. Actually, we went through them quite fast. All right, guys, before I start the exam, do you have any questions? Hmm. All right, then. What we're gonna do is gonna start simple. So I want you to work with me on this. So for each question, I'm gonna give you guys some time, and then I'm gonna just solve it live. And I just hope you give it a try because it's very important for you to pass. As these questions, as you can see, it's a lot of points, and it comes very often in exam. All right, so let's take mm, 5 minutes, and then I will I will basically solve this one. Guys, you know it's better to interact. It'll be helpful for me as well. Any ideas how to do this? Hmm. Well, if you guys are not answering, then I'm gonna go ahead and start, well, solving this. Well, I hope all of you can see the screen now. Yeah? Okay. So anyways, know that our sense is this one. And we have to show basically the first question says, okay, show that this R is the equivalent, right? Yeah. And in order to figure that out, we have to look at three things, right? So, first thing, we must show that R is first thing reflection. Secondly, we have to show R is symmetric and that is transitive. Yeah. So, in order to prove these, we have to just do something. And start with here. So, since n minus k is equivalent to itself, you can say that nk or nk is reflexive for all n and k's being part of our set set A. So this literally is enough to prove that it's reflexive. Therefore, so 1, 2, we have to show this symmetric. So let's suppose that we have n1, k1, k2 with k1 equal minus k2. And since I can say that they're equal to each other, I can say the other way around. So n2 minus k2 is equal to n1 minus k1. And where did I print this from? I got this from here. As you can see, it's written here and it's written in the exam as well that most of them are equivalent. Therefore, I can assume that this is symmetric. Well, let me write it down. It's symmetric. All right, this is the second one. Now we go to the last one, which is transitive. And then for that, we have to assume that we have n1, k1, and n2, k2, and a third variable. And n1, k1, no, actually, n2, k2, okay, are our new variable, or our new variable pair, very same. And because of this, we can say yeah, or and 3, this is equivalent. Therefore, from 1, 2, and 3 include that it's equivalent. Or Let's yes. And next question, basically B was asking us to explicitly write down all the different equivalence classes. And we give a complete system represented. Wow, great. So earlier I said it's very complicated when you read the description that they gave us with the slides, but you have to think of them this way. System representatives is system that includes pairs of distinct keys. That's all it is. What are keys? Possible combinations. Let's take a look at what I mean right now. Yes. So let's take a look at B. All right, so we have to figure out the equivalence classes. We know that A is 1, 2, 3, 4, and say 2, 4. Yeah. So now we have to do is take all possible combinations. So let's start 1, 1. Sorry, can be a set. So 2, 3, 3. Other set would be other combinations. So for example, combination of 1, 2, combination of 2, 1. And go 3, 3, 2. And then 3. And then this goes the same for any other combination. So you just enumerate them. For example, left and 3, 3, 1, 2, 4, and 4, 2. Okay. Um, of course, 1 second. So I'm gonna just finish enumerating all possible combinations. Feel free to do this however you want. Okay, so in terms of transitivity, so actually, this is something that will probably pop in the next in your exam as well. So let's look at all of them. So first of all, this reflexivity. The way we figure this out, we assume that since the equal itself, therefore, it has to be reflexive. Because for any itself being part of the set it's from, it has to be itself. So it's reflexive. It has to be equivalent to itself, that's what I mean. And goes for same goes for symmetry as well, as you basically take n1, n2, and then flip them and say because it's interchangeable, therefore we prove the symmetry, at least the property. And then when we go to transitivity, we just assume basically we know that there's n1 and k1, and we know that there's like 4 types of values for each variable. So we understand that there are many, many more iterations. So we can say that if case the first pair, so n1 k1 is equivalent to n2 k2, therefore we can assume that n2 k2 is equivalent to n3 k3, And by transitivity, the first n and the first k are equal to the third k, and you can say it's equal even to the last k. But it's always better to prove it this way. So we take first, second, third, and n plus one, n plus two. Transitivity. Is that clear? Yeah? Oh, okay. Great. So right now we have how many sets? So one, two, three, four sets of equivalence classes, basically. So now we're asked to create a complete system of representatives. What does this mean? This means we take a representation of each set. In this case, it would come down to, so this is A, this is B, C, and D. So those three. 1, 2, 3, 4, and 3. And this is basically the answer. That is the complete, no, bad handwriting. Complete system. Yes. All right. Great. Oh, go back to the slide. Okay, so I hope that made sense to everyone. These types of questions are quite common. Usually always says show there is an equivalence relation, and this is not very common in equivalence classes, but the relation definitely. All right, same goes for second question. Please guys, a bit of interaction would go a long way, helping us both. So I'm gonna give you 3 minutes, so up until 12:50, and then I'm gonna figure this out as well. Good luck. All right, guys. I think you didn't really try, but it's okay. I will go through it and hopefully it will be clear for you. So let me just share my screen. Yes. Great. All right. So second question. Those injections and surjections. So the first question says you have, well, each of the two functions defined below determine whether or not the function is injective or whether or not the function is surjective. So it's the same question for both. And first function we have, one second, there we go. F of n is equal to n minus 2. So first thing we have to show that this is injective and surjective, right? So take a look at f. So we know that f cannot be surjective, sorry, injective, because it's basic in absolute power, and we can imagine that there are probably two x's that are not equivalent, that are not the same number, that produce the same y when you put them in the function. So let's look at those because it's an absolute value. So let's start with the simple ones. Let's start with f of 1. So f of 1 is equal to minus 1, which is equal to 1. F of 2 is equal to 0. So skip that actually. And let's try f of 3. So 3 minus 2, that's 1. Absolute power of 1 gives you 1. As you can see here, f of 1 and f of 3 are the same. Therefore, f cannot be injective. And you can already see that because in absolute powers are used most of the time non-injective because they repeat the same value on different axes, obviously. All right, so let's take a look at surjectivity. So f, let's say I want to show that f actually covers the entirety of the codomain. So in this case, I know it covers anything bigger than 2 because it's a function we have. So we can imagine the function as this for any k part natural numbers, f of k plus 2 is equal to k, which is equal so to k. In this case, I'm showing basically that, hey, the codomain itself, it goes from 0 up to infinity, but in this case, we have n minus 2. So our domain is basically bigger than 2, from 2 on. And in this case, if we take any k that's part of a natural number and take k plus 2, we produce the same. So therefore, I can say that f is surjective. Yes. Sorry for the bad handwriting again. Almost like a doctor. All right, great. So I hope it was clear for these two. Because now I'm going to take a look at the second one. And the second part of the exercise says function g, c, students. or it's a natural number that assigns to every computer science student at who his or her student number. Oh, this is student number, and that these are the students. So let's take a look at this logically. So intuitively speaking, since different computer science students have different student numbers, so students has a student number for each student. There's an actual student number only for them, right? Specifically. So we know that they have a different numbers. Therefore, we can say it's injective. Well, from student to the student number, obviously, this direction is injective. And to check for subjectivity, you have to check number of students if it's finite and if the codomain of G is finite as well. So we know the student numbers are finite. Sorry, the student numbers are infinite because they're numbers that could be combined in any possible way. However, we know the number of students is finite. Therefore, it cannot be surjective because it doesn't, the function student number doesn't cover all the possible values of student number. Therefore, it cannot be surjective. If it was the other way around, so student number 2 see a student, then it would not be injective because each CS student will have a student, each student number would be owned by one CS student. Actually, it would be injective, but it would be the same non-surjective as well. If it wasn't grades, then it would be the non-injective flex. All right. So let's go back to the slide. And I hope that was helpful. Helped you understand. Okay, okay. Understand a bit more about injections and surjections. All right. So let's keep going with some exercises. This is function composition. This is very popular with the course. So it was in basically all the past exams. So I would really appreciate it if you would interact with me here so that I understand at which level you understand this, so that I can well do my job better. Anyways, do that. I will give you guys well 2 minutes, and then I'm gonna solve this, and then we can take over. All right, guys, time to, well, do this and then hopefully take a break. All right, let's see. You should be able to see my screen now. Great. All right, so yeah. Now we're gonna take a look at the third question. And the third question is actually quite good for point. So it's about function composition, as you know already. And the first one says, give an explicit description for f of x, the function f defined by f exp
Yeah.
2 with inverse and inside of both the inc. So the increments, we know that the inc is basically incremented by 1. Sorry, incremented by x, of course. We know the inverse of x is basically the inverse. And we know the exponential is basically the exponential, right? So here, we have to do is take all these three and combine them. And what we do combine them, then we start with the first expression. So the first expression we have is exponential. So we take that and we have to the power of x. And then we have this with inverse. And this translates to, by the way, this is not equal, it's just narrow. So this translates to 1 divided by 2x. And then because I'm basically trying to increment, and then this will become basically 1 divided by 2x plus 1. I hope you understood the order I went through them because that's basically the exercise. There's around 4 points, this question. And the second question is basically the opposite. So express So I'll have to express a function for g of x, g of x, speak of x now, x minus 1. So this is basically the opposite of what we did here. Oh, sorry, minus 2, excuse me. So we're gonna use these three to express this. How do we do that? So first, we notice the inverse. So we can say that g is an inverse of the exponential, since that's second in order, of, and because we incrementing on always add 1, right? And in this case, we have minus 2. So what we need to do is take inc minus and basically minus 2. Since we cannot write minus 2, we just put decremented by 1 and then decreased by another. And this will result in this. Yep. Okay, guys. So I hope that was clear enough. We are going to take a short break, actually. For around, wait, let me see what time it is. 13:05. So let's come back at 13:20, 15 minutes. We still have, let me see, we still have 1, 2, 3, 4. We still have 4 exercises. So I'll tell you what, yes, 1:20, and then we'll get to the end of this. All right, see you in a bit.
The recording has stopped.
All right, welcome back, guys.
This meeting is being recorded.
So, I hope you had a good break. So now we're gonna work on induction, everybody's favorite topic. All right, so since we don't have a lot of time and we have like 4 exercises to go through for each one, I'm gonna give you like 2 minutes and then we're gonna go through them one by one just to have enough time to explain them. Mm. All right, I'm gonna share my screen and then let's get going. All right, guys, so I already wrote down these. So this is our function, right? We have for each n, n plus 1 is equal to the n plus 2 to the power 2 times n plus 1. Well, first thing first. So we have two questions. The first question asks us to calculate the terms t2 up to t5. So using that question, we can we should immediately start, like whenever we see any question that looks like this, we should immediately just start calculating. And then we just immediately apply it. So t2 is equal to t1 plus 2, 1 plus 1. And we know that t starts t1 starts t starts at 0 and t1 is based on 0. So we know that t1 is basically equal to 0 and then 2 to the power 2 times 2, that's equal to 4. Or more appropriately, I'm going to write it down in the normal European form. Okay, with t3 it's the same. So it's equal to t2 plus 6 is equal to 10. Since t2 is already found here. The same here. T4 is equal to t3 plus 8 is equal to 18. And then t5 is equal to t4 multiplied plus 10. So 28. Very simple. So whenever you have these questions, this type of question, immediately just calculate them. And then this is where induction comes very useful. So this asks us basically to prove by induction that for each n, Tn is equal n plus 2 and minus 1. So, as always, first things first, whenever you see something like this, we start by base case. Base case is already given, t only 0. And we know that also if we replace 1 is equal to 1 plus 2 times 1 minus 1 is equal to 0 as well. Yeah. So therefore, this holds. Now, inductive case. So now we assume for all of them that for any m, Tm is equal to m plus 2 m minus 1. Of course, this is derived from this right here. This is just an assumption. Don't think about it, just assume. You just have to assume. Now, the proof step. Proof case, I guess. These are not the same names as in the course, but nonetheless, these are the 3 steps as always. So the proof case comes with Tm plus 1. And then we say, hey, we assume, we have to always say that we assume. And therefore, now we have to prove that Tm is equal to, Tm plus 1 is equal to Tm plus 2m plus 1. This is, of course, comes from here. And then, since we already have m from our assumption here, then we're gonna use that. And our Tf basically become 2 m minus 1, 2 m plus 1. And of course, this is definition. This is just inductive. And this gives you, just calculated, m times 2 plus 2m plus 2. In general, m. Okay, so basically here, we say, hey, this, there exists m plus 1. And using induction, we prove that for all m plus 1, there exists e is equal to m plus 2 m minus 1. Therefore, dot t minus 1 this is just a translation of this, but it's equivalent. Yeah, and that's basically the exercise. Huh. Okay. All right, guys. Yeah, it took me longer than I expected. Anyways, let's take a look at sets now. For sets is quite simple. They're just gonna ask you to draw some Venn diagrams and then basically prove some theorem. And since we don't have so much time, I propose they just start it. So as you can see, you have to basically draw these two. So let's start sharing. So for sets, for sets and Venn diagram, so basically two questions. First thing, let's draw Venn diagram or B without, well, yeah, B excluding A union C complement, and for B excluding A complement, union B excluding C complement. All right. So in this case, they say you have to show the steps in between. All right. So first things first, start by depicting a diagram, and we start by the smallest selection. So we have A union C, A, C, and let's say A, B, C. A and C are those. And then from here, we have to give their complement. So the opposite of that, what's that? Everything else. And we have A, B, C. And then the complement is basically everything else, apart from the actual A and C. So we don't even touch stuff they share and everything else. And then from there, they said B excluding. So at the moment, we have A union C prime. And I want this to become B excluding A union C prime. So what I do is I kind of create a new one. And this is B excluding that. So as you can see, B was this. And now we have to basically take B excluding the complement. So excluding this and excluding this. And then we take what's in B. So again, A, B, C. And to present this, you basically have to look at here and do the opposite. So what's still in B but not here? Only these. And that's it. All right. Now take a look at the other one. Our other graph is basically saying we want B excluding A and union B excluding C. So start with a normal Venn diagram. Then we only take, first of all, we start with A complement. So everything else. And then B excluding A complement. So B excluding everything else apart from A, which leaves us with this. And this is B excluding complement of A. As you know, like basically the complement of A is everything else. And then B excluding that is basically only this bit, the intersection. And for C prime, we do the same. So for C prime, C complement basically everything else that's not C. And then from there on, no, apologies. Yeah. From there on, we can build B excluding A complement and B excluding C complement. And that will be basically combination. Oh, sorry. Hmm, BC. And then basically, as you saw here, took that small bit. We're gonna do the same for C, and that will basically, since we it's the same formula, and then we unionize both, and then we take from what's in B and C. And that's basically it. Yeah. And now take a look at the B question, which says prove the set theoretic equality displayed above. For that, we have to look at definition. So we look at B, excluding A, C. And now, by definition, we know that this means B intersection with the opposite of that, right? Because B excluding what's inside the complement of A union C is equal to B intersects with basically A union C complement the complement. And therefore, this by definition, of course, this will become like this. Oh, and then, of course, it opens up, and then you can basically take both visually, distribute them, and then we're gonna basically, by definition, say that we're taking the complement of the complement to take the original A. This is union. We do the same for the other one. C is the complement of the complement. And this will give us basically something similar to what we had up here. And then we can say that this means that B is itself excluding A complement and excluding C complement. Yep, I hope that makes sense. All right. So those two questions are quite popular and they always pop. So they will definitely be there. Okay. Take a look at the next one. ordinal relations. Probably didn't think that this will pop in the exam, huh? Well, it does. I will give you guys minutes for 42, and then when I'm do this one. All right, guys, I'm gonna start sharing my screen and showing you how to go about this. So basically, here you're asked to construct a Hasse diagram of the partial ordering relation of A on the set B, and it's given right there. And they're asking us to explicitly, yes. All right, so question 6. There we go. Okay, so question 6. Let's start with A. So ask us to explicitly write down the sets Gx and Hx, right? And to simplify the notation, you can just write them as sets. Great. All right, so let's start with writing down the set of 12. So G12, since we're asked to basically construct the partial ordering of A, we'll have to take basically all of these values. And these are shorthand, by the way, for 1 to 3. So this is the same as this. So 1, 3 is the first graph. 3, 3, 1, and 3, 2. All right. And then you construct for the next one. 3 and 32. And then, of course, you're gonna go 21. And then that will, it's getting too big. Okay, 13, 22, 23, 21, 22. By the way, I keep saying 13 and 22, but that's just for myself. These are states, of course. There's 1 and 3, 2, 2, of course. I hope that I didn't get you confused there. 23. And of course, 23 is empty. Empty set. And it's the same for 32. After 31. You basically have the same. All right, and from here, we can use our graphs to basically create a hashtag diagram. We'll start with 12, basically 13, 2, 1, 13. We don't do anything. This one. And then try to 21. From here, we still have the same. Goes for 22 as well. Unless it's 23 or 32. Then these will be equal to the empty set. By the way, this notation is not, I wouldn't advise using it. You should always write each one in its own line during the exam, especially. Two. Yeah. Therefore, you can look at all of these states and basically you can construct a diagram from here. And for the diagram, I'll actually try to make it a bit clearer. 1, 3, 2, 3, 2, 2, 2, 3, 1, and 2, 1. So we know that 1, 2 connects to 1, 3. No, 2, 1 connects. We know that 1, 2 connects to 2, 2. We know 1, 2 connects to 3, 1. And 2, 1 connects to 2, 2. And 3, 1. Sorry for the mess, but basically everything here connected to everything here. And this goes the same for here. So this is connected to both. And that is connected to both. This is connected to both. So this way, basically, you can make sure that the following sets, Gx and Hx, perform the Hasse diagram and make up the Hasse diagram. And you can for sure see how is partial ordering relation. And it's less than A, which is relation A says that A and B have to be less than C and D. Well, yeah. So we follow that relation basically to come up with this distribution. And then from here, we pick the ones actually desirable. And then we just get the graph. I hope that makes sense. All right. So this brings us to B. The question B.
So, guys, I think he has some problem with his laptop. He'll resume like the meeting in a bit.
I would think, okay, now it's back. Huh. Wow. Apologies, my laptop is going a bit crazy. All right, so we were here, right? And now I'm gonna get back to sharing my screen and let's finish the sixth question. Okay, so the sixth question is actually quite intuitive. Oh, sorry, the B section of the sixth question is actually quite intuitive. It says, hey, does the set B have the smallest element according to the relation less than A, which is the relation I told you about earlier? And if so, please give the smallest element. If not, please list all minimum elements of B. So obviously, we already have B, and we don't have to look far away, as we see here, which are the most, well, the smallest elements. And these are these two. So B, smallest elements of, of combination between the two sets is 2, 1, 1, 2. It's literally the smallest, that's all they mean. In terms of C, they say, does the set B have the largest element according to the same relation? And if so, please give the largest element. Otherwise, all of them. And this is the same. There's the smallest, there's the highest. Because this is 3 and 2, which is higher than anything else. Quite simply. 3 and 3, 2. These are the largest. All right, great. So I hope that makes sense for you. This part, I don't know if it makes sense for you or not, but it's not very challenging, the graph itself. As if it gets you confused, you just need to practice a bit. And usually after the fourth time, you basically can do this off the back of your hand anytime. And these questions were actually worth quite a good sum. These were worth 10 points. So yeah, it's a lot. All right, this brings me to the next question. And it's a function that combines functions and equivalence relation. Sorry, it's a question that combines both. Two minutes, and then we're gonna try to, well, we're gonna finish this one. All right, guys, let's finish this. We have a chunky exercise at the moment. So let me share my screen, and then I hope you had enough time to actually look at this question. Well, this exercise and these questions. Okay. Great. So now we're at question number 7. Good job, guys. It was a lot. Anyways, for this, they gave us basically has final grade, which is a set made up of X and Y pairs, of course, X being the student and Y being the grade. And it said for each of the relations has final grade and the opposite of it, and basically the complement of it, decide whether it is a function or not. Please verify and explain your answer. Where has grade, oh, let me write it down properly, as final grade, and this is equal to basically X, Y, X being student, and this is being the grade, and formally speaking. All right, so A, we know that since every student is assigned exactly one final grade, has final is a function, because if you put any X, then it will output a Y, and the X is always distinct. On the other hand, there must be at least one grade that is obtained by more than one student. So basically, you can say that has final grade is a function. And theoretically and practically would be right, correct? However, its complement cannot be a function because for each grade, there exists more than one student. So for each f of x, let's say this is equal to f for now. F of x, there's 1 second. Yes. So for each f of x, there is a y. However, for f complement of y, there isn't one x because there are multiple students, x1, x2, x3. Therefore, this is not a function. All right, let's go to B. Next, consider the relation R has final grade complement and has final grade. These show that R is an equivalence relation. We did this already, right? So, as always, R has to be reflexive, symmetric, and transitive. Helps to keep the order, of course. So we know reflexivity. We know that every student receives a final grade. So for every X, there's a Y, such that X has the final grade Y. But also for every final grade Y, the complement of has final grade is an X. Hence, by the definition, we can say that X are X. If you put as final grade and basically as final grade, sorry about that, -1, then this would make sense. So there's a Y in the middle and then X. Yeah, great. That's 1. So 2, we have to look at symmetry. So we suppose that there's an X or Y, so a student and a grade. Then by the definition of the relations, we know there exists a grade Z such that X has final grade Z. Z, Z is final grade complement Y. Then we also have Y has final grade of Z and Z as final grade complement of X. Therefore, Y could be considered Y or Z because has final grade is symmetric. It goes both ways. And this is 2. And 3 is transitivity. So we suppose that we have a student a relation, which is HFJ in this case, but anyway, this relation to Y. And Y we have a relation to Z. Then we know that there are grades U and V such that X has final grade U and U has final complement Y and Y has final grade V. So what I'm trying to say is basically you can translate it. There's U and V such that X has final grade U Y, and then Y itself has final grade V, and V itself finally itself is the grade of Z. So we know X could have the grade U and U could be the grade of Y as well. So we know this for both cases, and therefore we know that it's transitive. Because now we can say like it follows that X has final grade U and U, which is the grade is, is obtained by the student Z. And this is 3. From 1, 2, and 3, we conclude R being being basically both our functions is equivalent. Nice. So from there on, we know that they're equivalent and we know about the first one, is function or not. And now they ask us to describe in words what the partition into equivalence classes induced by R looks like. So they want us to basically create the partitions that they have, the classes they have in common and how they differ from elements in a different equivalence class. But for this question, we can say that R partitions the set of students into equivalence classes in such a way that students in the same equivalence class all have the same final grade. Remember, whenever you make equivalence classes, they always need to be having the same amount, the same value at the end of the day, like we did earlier. So in this case, it's the final grade, and the students in different equivalence classes have different grades. And of course, you can write it down such as R is class let's say R1 if and only if R1 is different from R. And this goes the same for any other R. 2, 3, in general. Well, guys, that's it. It's been a lot of questions and many types of them, and I hope that helped you prepare for the exam and understand what's expected of you. Otherwise, do you have any questions? Is there anything that's not clear for you guys? Can you say at least what's clear for you so that we can get some feedback?
The recording has stopped.
Oh, it's fine. Let's see. Maybe more have guys that will reach out. Okay, fair enough. Fair enough. Well, guys, it's just about practice. It's nothing more. It's quite